Now we look at the matrix of the dual map and how the matrix of T prime is related to the matrix of T. And if you think about what you know from your first linear algebra class for a moment, you realize that there's a missing ingredient that we haven't been talking about up until now, and it is the transpose. So the transpose of an n by n matrix A is denoted A with this book uses a superscript lowercase t. And this is going to be an n by m matrix. And it's going to be the one whose jkth entry is the kjth entry of the original matrix. And if you recall your properties of the transpose, you know that the transpose of a sum is the sum of the transposes. And if you transpose a scalar multiple, that's just a scalar multiple of the transpose. And that if you have a matrix product, so assume those things are the right size so that the product makes sense, then the transpose is going to be C transpose A transpose. And for this one, you might want to look back and think about 3.103. Okay, so that was in the last clip, right? So now let's look at 3.114, which says that for a linear map from V to W, the matrix of its dual is the transpose of its matrix. And so I think actually thinking about matrices clears up a bunch of the stuff about duals. So for example, some people tend to confuse the dual with the inverse, but you can see that the dual always exists, right? Duals always exist no matter what. Inverses don't always exist. You need injectivity and surjectivity and blah, 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 and there's a whole bunch of conditions. Oh yeah, okay, maybe I'll just leave it there for now. Okay. So how do we see this? Well, let's take A to be the matrix of T, and let's take C to be the matrix of the dual. So then we need to show that C is equal to A transpose. In other words, we need to show that CKJ is equal to AJK, or vice versa, whatever. Okay, and so in order to do this, the connection between transforms and matrices is always given by a basis. So let's write down the notation for our bases. So we're going to take a basis of V's, and a corresponding dual basis of phi's for V prime. And then I'm going to take that whole thing and duplicate it so that we get some W's, which are going to be our basis of W, and then dual basis of size for W prime. How's that for lazy? Okay. Then let's see. So by definition, and in particular by the definition of the matrix for T prime, which we're calling C, psi j composed with t. So this is t prime psi j is the sum of, and then we'll use r for our index 1 through n, c r j phi r. So that's hold on just a sec. Wait. Phi or psi? We got going from phi to. Yes. Yeah. Okay. Just had to make sure that I was using the right Greek letter there because I wanted to make sure that the map is doing the right thing. But we are going from w prime to v prime, and the basis of v prime are the phis. Okay. So we've got this right. So let's see now. Let's apply this godforsaken map to an element of the v basis. So applying this map to a vk, what do we have? Well, on the left side we have phi j compose t applied to vk. So that looks like this. And then on the right side we have the sum r equals 1 to n c r j phi r applied to vk. And then by the definition of the dual basis, you remember how all this shakes out. Basically, this part right here is going to equal 1 for when r matches k, and otherwise 0, and we just get that one single term out of the sum. So that's going to be the CRJ when r is equal to k. All right. Fair enough. But we have another way to compute phi j of tvk. So by the definition of the matrix for T, which we're calling A, we also have that phi j of tvk, so this thing we just computed in the last line. So these are the same. This is, let's see, so that's phi j of, and then I can use the definition of T, or the matrix for T, to write this in terms of its matrix entries. So this is sum r equals 1 to m, a r k w r. And so let's see, so this is going to be now the sum, whoops, r equals 1 to m, and now we use the linearity of the phi j's to factor through the linear combination here, and we have psi j on wr, and then we have, so that was by linearity of psi j. And then we once again use this dual basis thing. Now the dual basis psi, and what happens, we're going to pull out the coefficient where r is equal to j. And since we already noted back here that these two things are equal, that gives us that these two things are equal here at the end, and that's what we had to prove.